Cool. Questions overall on how the class is going and any of the material we've covered so far. So I do have office hours. Oh, sorry, go ahead.
When we're evaluating any sort of value using Stokes' theorem, we're not evaluating any sort of distribution over the domain, right? We're just determining like the average value of like, say, vorticity over a domain, right?
I'm not exactly sure what you mean, but let me draw out some stuff. So Stokes' theorem says if we have a surface like this and a unit vector that comes out like that, let's say we're talking about velocity or something like that, okay? Then this surface is S and the contour around it is C, where I'm integrating in this direction. Stokes' theorem says that the integral of n dot del cross, let's say velocity v ds, evaluated over our surface, is equal to the contour integral around that surface. And so I'm not sure exactly what your question is. I think if I had to guess what your question is, what we're integrating on what we're calculating on the left-hand side is, for instance, this might be a vorticity if v were velocity, right? Then you're basically totaling the vorticity over this area.
No, that's
something like an average, but multiplied by the area, if you will.
Okay, no, that's what I was trying to like wrap my head around, because like, for instance, we're already past the homework deadline, but like if we have like a given surface and we have like a vorticity, right? Like taking the surface integral is not going to give you the vorticity distribution. It's going to give you the total vorticity over that entire domain.
That's correct.
Okay. Yes. I just wanted to kind of.
Can I get a few more videos on, please? Again, as I mentioned at the beginning of the class, I don't expect all of you to always have your videos on at all times, but it'd be nice to see a few more of you. I do have office hours after this. Immediately after this class, I'm just going to stay on. I'm probably going to stop recording at that point, but I'm just going to stay on. It is specifically designed to be after the homework deadline, so that the office hours are designed to have you guys ask me questions about the class, sort of like what Nikhil and I were just going over and stuff like that, rather than specific problems on the homework. Hopefully it'll be pretty barrier-free. If you're interested in hearing from me in office hours, then just stay on. I will actually ask some of you guys to indulge me. I have no idea how well the class is going right now for all of you guys, given that I see a very small fraction, that I've seen a very small fraction of you. I could do like an anonymous poll if you're not comfortable, but you could also just come to office hours or just stay on after the call and just tell me how poorly I'm doing, or how well I'm doing, or if you're using the notes, if you're watching the recordings, if you feel the homeworks are going okay or something like that. If any of you are willing to indulge me for that reason, I would really appreciate it. I also barely know any of you, but part of the reason is because I don't really see you guys all that much. Please, if you're willing to, stop by office hours, and by stop by I just mean don't hang up at the end of the call. Okay. Here's where we've been so far. We're talking about basically a fluid that's resting in between these two plates, and then at time t equals 0, the bottom plate is pulled to the right-hand side like this. Okay, and then we set up the problem that looks something like this, where this is the partial differential equation. This comes about by reducing the Navier-Stokes equation with 3 boundary conditions: an initial condition that says that the fluid is at rest initially, and then 2 no-slip boundary conditions at the top and bottom plates. We started to introduce this new method called the FFT method. First, we actually decided to do a different problem where instead of the fluid initially being at rest, we're saying the fluid has reached some sort of steady state where the bottom plate is actually pulled to the left. So you have this linear profile, and then we're trying to see how long it takes for the fluid to stop, or how the flow eventually becomes how the flow eventually becomes at rest when the two plates have been asked to stop moving. In this FFT method, to calculate this the solution to this new problem here, what we postulate is that the problem can be written as a sum of coefficients of basis functions. The basis functions are functions of y, and so then the coefficients can be functions of t or just basically anything else, just not functions of y. The analogy of this was that these basis functions are kind of like unit vectors, and basically any function can be written as can be expressed as a sum of various various basis functions, just like how any vector can be expressed as a sum of various vectors. And so the game that we're trying to play now is to try to understand what those coefficients are, because just like how a vector is completely determined by its coefficients of unit vectors, a function could also be determined by its coefficients as well in this sort of new basis set, if you will. Okay. Now, of course, a function has infinitely many values between 0 and 1 between our two boundary conditions, and so therefore we might expect that the sum also goes out to infinity. Okay, and so we're going to have infinitely many equations, but that's okay. Okay. To remind you, we introduced this concept called an inner product, which is basically just the two functions multiplied together, integrated from 0 to 1, and it behaves essentially like a dot product, where all these basis functions are orthonormal within 0 to 1, kind of like when you take a dot product. If you dot two unit vectors together, you get the Kronecker delta. Same thing over here. Okay. And then it turns out that if we then transform this equation by taking the inner product of both the left and the right-hand sides of that equation, the left-hand side was this, dg dt, and the right-hand side is d squared g dy squared. If you transform both sides, then you can simplify this PDE into something that we can actually solve very easily. Okay, left-hand side looked like this. The right-hand side, we had to do some integration by parts, but eventually showed that this actually simplifies the equation significantly. And then we arrived at something like this for the right-hand side. And then we were able to transform our partial differential equation into something like this. Okay, any questions at all on how we arrived at this point? Now, once we get to this point, and if any of the stuff up here seems unclear, it should actually, because I haven't really talked very much about the theory or why I was able to do this. For instance, where this whole thing came from with the basis functions, right? How come when I did the integration by parts, I was just magically able to call some things equal to 0, right? You know, it kind of seems like black magic right now, and hopefully it should, but over the next few lectures, it'll hopefully become more clear, okay? And so, but, you know, taking all of that on faith at this point, all right, we've reached this point right here where, again, the game is to try and figure out the values of these coefficients. And so now we actually have an ordinary differential equation for these coefficients. Okay. Remember, the coefficients could potentially be functions of time, right? And so it's okay to have a differential equation in terms of those. And now we basically just need to solve this differential equation. Okay. Now, to remind you, for a differential equation has no solution until it has the right number of boundary conditions, right? Can't have too many, can't have too few. In this case, we have one derivative in time, and so we need a boundary condition in time, okay? To find that boundary condition in time, we will actually use some of the original boundary conditions in our problem. You can kind of see what we're gonna do here a little bit, because in our FFT solution here, you might recall one of the ways that we were able to make one of these terms go to 0 is we applied two of the boundary conditions. We applied boundary condition 1 and boundary condition 2. There's one other boundary condition that we have not used so far, and that's the initial condition. The initial condition says that g is equal to y minus 1 at time t equals 0. Okay, and this initial condition actually says something about g at a fixed time too. And our solution right here, or our differential equation right here, is also in terms of time. So that's another clue that this is maybe something that we're going to use. Okay. Now, of course, the initial condition up there was that g is equal to y minus 1 at time t equals 0. Those conditions are in G. We're talking about G there, right? We actually need to talk about what happens to the when we express it in terms of these basis functions now, right? So we need to transform our boundary condition into this sort of basis function idea, and then sort of figure out how these coefficients will actually then behave in our ordinary differential equation. Okay, so we'll say find BC for this ODE by transforming the original initial condition. Okay? To remind you guys, the initial condition was that at time t equals 0, we have that g of g at y of t, at y and t, so at y and 0 is equal to y minus 1, right? And so what this means then is that gn evaluated at time t equals 0 here, to make it even more clear, I'll write this. Evaluated at time t equals 0 is equal to the inner product of g evaluated at t equals 0 and one of the basis functions. Okay? If you recall, that's because of this relationship right here, right? Gn of t is equal to the inner product of gy t and a basis function, right? And so we're basically just using that right here with a special case at time t equals 0. The reason why we want to do that, or how this is useful in this case, is because we know what gy of 0 is. That's this, okay? And so we can basically just figure out what the value of this integral is immediately. This is equal to that. G of y0 is equal to that, okay? And then the basis function itself is equal to this. Okay? And you can evaluate this integral. Okay, this is something you can stick into Mathematica, or if you actually want to do it by hand, that works too. I won't bore you with the details for how to evaluate this integral. The value is this. Okay? And so now we have one first order ordinary differential equation and one boundary condition. And so we should be able to solve those differential equations, right? Now we do have infinitely many differential equations, right? There's one equation here for n, another equation, or one equation for n equals 1, another equation for n equals 2, et cetera, et cetera, et cetera, right? But we can just leave it in terms of n, and that's totally fine, right? So the solution of the ODEs looks like this. Okay, to solve this equation, does anyone just shout? Does anyone have any idea how to solve an ordinary differential equation like this?
Separation of variables.
Just separate it, right? So we multiply both sides by dt and then divide by gn and then integrate both sides, right? So we have dgn over gn times negative n pi squared dt. And we're going to integrate both sides. Okay, you end up with a log on the left-hand side, and then all that stuff. I can not deal with the log and stuff. You guys have probably seen equations like this, and so I'll go ahead and skip to what the actual solution looks like. Okay, maybe most of you believe me that it looks like that, right? It's a first order differential equation. It's just an exponential solution. Okay, and then this is where that boundary condition comes in. Okay, so this and now this is where we kind of go back and then look at our overall solution. Remember, the initial claim was that we can write our solution as a sum of gn of t and phi n of y, right? And as a sum of basis functions. And so now we actually have an expression for gn of t. In other words, we found the different coefficients of our function. And so now we've essentially solved the problem. Okay, putting it all together, the overall solution looks like this. Okay. Now, some of you guys are going to stare at me and be like, well, that's a stupid solution, right? I have no idea what that even looks like right now, right? Doesn't look like a parabolic whatever. We don't even have an error function. An error function was already kind of annoying enough to deal with, and it doesn't even look like that, right? And so what's up with that? I don't have a good answer for you if that's your question. That's just what the solution actually is. Just like how a vector is a sum of different things that's added together, in here it's an infinite sum. The nice thing about this infinite sum is that it converges, and so you can evaluate several terms, and then when you decide to stop, then is when you stop, and then the more terms you evaluate, then the closer, then the better of an approximation you get to your actual solution. I have some code that will actually plot the solution. That's how you look at what these solutions will look like. Okay, but I don't have it with me right now. I'll do it at the beginning of next lecture. Okay. But the way to actually, like I mentioned, the way to actually look at the solution is to basically go into MATLAB or Excel or whatever code you can do, and then just add together several of these terms and then plot it. Okay, and so in that code, that I'll show you guys, and I'll try and post it online. In that code that I'll show you guys, it'll just be in MATLAB basically. It'll evaluate the value of this function at various t's and y's, and then basically plot it. And so you'll see a 3D plot and stuff like that. And then the idea is that it'll evaluate the sum end here at various values of n, pi, and y, or at various values of n, y, and t, and then sum over all the n's that I decide to include in my sum. Okay. Let me go back and close the loop in for just 1 second. Okay. We decided to solve this particular problem, right? This is a related problem to what our original problem was. Some of you guys might be wondering why we did that. I'll get to that a little bit later on. If not today, then a little bit later on. But these two problems actually are pretty related. If we wanted to know the solution to this particular problem, I called this problem F, the other one I called G, right? The two are actually related. Let me show you how, okay? So it turns out or here, I'll call it like this. I'll say consider f of y of t is equal to 1 minus y plus g of y of t, like that. Okay. I'll explain why in just a second, why I'm doing this. Okay. But if you think about it, this function actually satisfies the partial differential equation, right? Let me go ahead and take this right here and bring it a little bit down here so that we can see what it looks like. Okay, that was the original differential equation. Okay. And then the equation and boundary conditions for G looks like this. And so let me copy and paste that here as well. This is totally something that's not possible on a chalkboard. So it's kind of cool. Okay. So here were our two problems, our two problems that we had. Okay. The reason why I copy pasted them over here is because I want to point out that our solution, or that our solution here for G, or the solution that we want, which is 1 for F, can actually just be written in terms of our solution for G, like this. And the reason we're able to do that is because this particular solution actually satisfies both the partial differential equation that we cared about and all three boundary conditions. Okay? If you don't believe me, let me show you. Okay. df dt is just equal to, well, the right-hand side of this derivative. That's just equal to dg dt, right? And d squared f dy squared is just equal to d squared g dy squared, right? Because the second derivative of 1 minus y is just equal to 0. Okay? Now, at time t equals 0, then f of y at time t equals 0 is equal to 1 minus y plus g evaluated at time t equals 0. But according to this initial condition, that's just y minus 1. And so therefore that's equal to 0. Okay? At a position y equals 0, f at y equals 0 is just equal to, well, 1 minus 0, whoops, sorry, 1 minus 0, because y is equal to 0, plus g evaluated at y equals 0, and that's equal to 0. Okay? And so therefore that's equal to 1. And then at y equals 1, or h, I'm being fast and loose with the squigglies, but hopefully it kind of makes sense, right? F of y equals 1 t is equal to, again, 1 minus y, but y is 1, so 1 minus 1, plus g evaluated at y equals 1, which according to this boundary condition is equal to 0. And so that's equal to 0. Okay? And so it turns out that our solution here, as we wrote down f of y of t right here, which is 1 minus y plus g of t, like that, that satisfies all three boundary conditions from our original problem. See this right here. This is the initial condition at time t equals 0, f equals 0. Boundary condition 1, which is that at time y equals 0, or at position y equals 0, f is equal to 1. And boundary condition 2, which is that at position y equals 1, f is equal to 0. Right? And it also satisfies our initial differential equation, because df dt is dg dt, and d squared f dy squared is also equal to dg dy squared. And of course, we know from our solution over here that g also satisfies the PD, and so therefore this also satisfies the PD. And so this solution, this is our solution actually. Okay? And so this is how we were actually able to do this. Conceptually, what we've done is we've broken up the problem into two components, if you think about it. Okay? Our two components look something like this. The solution for G is basically you have two plates, same geometry as for F, but then this bottom plate is pulled to the left before time t equals 0. Okay, And then we're seeing what happens when it comes to rest. And we're adding that to another solution, which is 1 minus y. That corresponds to basically a constant. Here, let me draw out everything again so that it makes more sense. What we have is basically f is equal to 1 minus y plus g of y of t. Okay? 1 minus y looks like this. That's the flow profile at steady state, right? G of y of t looks like this. This is what happens this is what you get before time t equals 0, or I'll say t is less than 0. And then at time t equals 0, everything comes to rest. Okay. And of course, the solution that we cared about is nothing is moving initially, and then at time t equals 0, the bottom plate is suddenly pulled to the right. Can you guys see how this actually matches up exactly when I add up everything? Before time t equals 0, these two things exactly cancels out. And so I have nothing over here. So nothing is moving. And then once time actually begins at time t equals 0, okay, then I'm basically adding the fluid slowly coming to rest over on the right-hand side to my steady state profile here to get the profile that I actually care about. Okay. This works out in general because the partial differential equation is linear. Okay. In other words, if F1 and F2 both satisfy the PDE, then so does F1 plus F2. And so we were strategic in how we picked F1 and F2 in this case. In this case, F1 was just 1 minus y. It was a steady state solution, okay? So here, we let F1, in this case was 1 minus y, a steady state solution. Okay, that satisfied the original boundary conditions. Okay, remember the original boundary conditions were that f is equal to 1 at y equals 0 and f is equal to 0 at y equals h, or y equals 1, right? And so you get a profile that looks like this. Sorry, I'll scroll down so you guys can copy if you want. It's still down here. Okay, this satisfies the original boundary conditions right here. Okay. And so once we did that, then we were able to solve a slightly simpler problem that has 0 boundary conditions, but this has a different initial condition right here. And then we were able to add those two together to get to the solution that we actually cared about. Okay, and this is a kind of a neat trick that that makes some of our problems a little bit easier to do at times. Okay. Any questions about how we were able to break that problem down? That kind of makes sense? Now, some of you might ask, did we actually even need to do the problem like this? The answer is no. And then later on, probably sometime on Friday, I'll actually show you how to solve this particular problem without having to do this sort of breaking it up. It doesn't really matter whether we decide to break it up or if we decide to do it like this. There are advantages to doing it like this. It turns out that in the FFT solution, it is convenient to have zero boundary conditions, to have boundary conditions that are all zero. For example, in our integration by parts step up here, we were able to turn one of the, to basically set one of the terms equal to zero because of the zero boundary conditions, right? But I'll show you guys in the future sometime like next lecture that's not completely necessary, okay? But before we really, so I guess I'll write down the overall solution now, just for posterity. For the original problem. Here, I'll just say for the original problem. The solution looked something like this. And the way we do this, again, is that we calculated a solution that looks like this using FFT, and then we just added our steady state solution to that. Okay. And again, we can try and plot this later on and stuff, and I should be able to show you that this looks that this totally works out okay. Okay. So let me summarize our overall solution method for FFT, because in the next homework and then maybe an exam or something like that, you guys will need to know how to actually deal with problems in this solution method. Okay. Okay. It's in 4 steps. The first step is that we postulate the solution as a sum of basis functions. Along one dimension. In other words, the basis functions are a function of y, for instance. Usually that dimension is the spatial dimension. Okay. If you have multiple spatial dimensions, then you can pick one. Then you should just be able to just pick one of them. Okay. But this is the point where we said f is equal to that over that infinite sum. Okay. The second step is to transform the PDE into an ODE. And we do this by using integration by parts and applying the boundary condition. Okay, someone asked, how do we know what basis functions to use? I'll get to that in a second. Okay. And applying the boundary condition. Okay. And the result of that should be, that the ODE should be for the coefficients of the sum. Okay. The next step after that is to transform the other boundary conditions of the PDE to give boundary conditions for the ODE. Okay, and then the last one is should be the easiest actually. It's basically just to solve the ODE and then plug into the sum. Okay. So in this 4-step solution, if you have that on a piece of paper next to you, because it's going to be hard for me to scroll back and forth, I just want to show you how we actually went about that in the example that we did. Okay. So the first step was to postulate that the solution is a sum of basis functions. That's basically what we did here, and we need to pick the basis functions that works out for our problem. I'll get to that in a second on how we actually pick these basis functions. There's a lot more that actually comes about here. Okay. The next step then is to transform our differential equation right here, into an ODE. And so that's where we took where we multiplied both sides by phi n of y and then took the integral from 0 to 1 of both sides. Or in other words, we took an inner product of both sides. Okay. And so that's where we got the left-hand side is just equal to this. And the right-hand side, we had to do this integration by parts sort of thing to get, and then show that both these terms are equal to 0. That's where we applied the boundary conditions, right? And then we were able to get to this, to this ODE right here, right? The third step was to transform the other boundary conditions that we did not use. So here we used boundary conditions 1 and 2. We did not use the initial condition. And so today, the first thing that we did was we transformed this initial condition into a boundary condition for the ODE, or an initial condition for the ODE, whatever you want to call it. Okay. And then it was just a matter of solving for the ODE, or solving the ODE, and then finally plugging everything back into our sum. And then, of course, you can do all the things that you would normally do. You can analyze this, you can calculate forces, you can do all that sort of fun stuff that you would in a normal fluids problem. Okay. Now, I got a question. What are these basis functions? Because the basis functions really are sort of the magic of this whole thing, right? The basis functions allow us to, they're orthonormal, right? And so they allow us to express things as a sum like this, right? They allow us to, cancel out some of these terms and make them 0. They allow us to do this sort of funky thing right here during the integration by parts step, that to basically take the second derivative and turn it back into something into its original form right here, right? And so the basis functions really are the magic of this whole technique. And so the question is, what are these basis functions? Okay. Now to do that, let's actually look at that integration by parts step, okay? And that'll actually give us the sort of necessary requirements for something to work out as good basis functions. So let me just write it out again. I'm not going to copy paste this time. We had to integrate by parts twice, right? The first term looks something like this. The second term looks something like this. And then, of course, we had this guy right here. Okay. And we were able to then reduce this down to several things, okay? We were able to show that each of these terms over here, for various reasons, turned out to be 0. And then we were also able to drastically simplify this last term right here. Here, I won't write that to make it confusing here. Okay. And the way we were able to make all these simplifications is specifically because of the basis function. Okay, and so this is how these are sort of the necessary properties for the basis functions. Okay. Basis functions must satisfy three properties. Ugh, sorry, can't write today. Okay. Number one is they must satisfy what's called an eigenvalue problem. Okay. That's just a fancy word for a special type of differential equation. Okay. The differential equation that we care about looks like this. Okay. This is not a differential equation that you guys recognize because it's actually just a very general form of differential equation. Okay. I'll say where L of y is a second order differential operator for the FFT variable in the PDE. Okay, that's a really confusing way of saying, here's our original PDE above. Right? And so here, our differential operator is that. Okay? So in other words, so we must satisfy basically this equation. Okay? And that was how we were able to get to convert the second derivative into, well, just the original basis function with something in between. And this something out, or this something out front is our lambda sub n. It's just a constant. These lambda of n is just a constant. Okay, these are called the eigenvalues. Lambda n is called the eigenvalues. That's why this is called an eigenvalue problem. Okay, if you don't believe me, these basis functions, well, we calculated that up here, right? Let me scroll really quickly. Right, the second derivative right here can be written. Our basis functions were square root of 2 sine n pi y, right? If you take two derivatives of square root of 2 sine n pi y, you get negative this sort of stuff, which has a sine n pi y in it, and so it's written in terms of this basis function right here. Okay, and so that requirement for the basis function is what allowed us to reduce this down right here, right? So this is where requirement 1 comes in. Okay. The second condition is that they must satisfy boundary conditions of the same type as our original problem. Okay. There are three types of boundary conditions that are found commonly in these sorts of problems. You don't really need to know what they're called, but one of them is called Dirichlet, like that. And it's just that. At y equals 0 or y equals 1. Okay. This is as opposed to other types of boundary conditions, which we could potentially find, and you will have to solve some problems that look like this, where instead of the value of the function being 0, it could be that the value of the derivative is equal to 0. Okay. And then there are also boundary conditions that are, this is called a Neumann, the second one's called a Neumann boundary condition. if you want to know how to pronounce it. The third one is called a Robin boundary condition. And that's basically that the sum, some linear combination of the derivative and the original thing is equal to 0. Again, at y equals 0 or y equals 1. Okay. Here's what I mean when I say that the boundary conditions have to be the same type as our original problem. Our original solution, or our original problem looked like this. We have two boundary conditions here in the variable that we did our FFT, right? Our basis functions are in terms of y, and so there's the two boundary conditions right there, okay? Both of these boundary conditions say that g is equal to 0, or g is equal to something, not that the derivative of g is equal to something, okay? And so we have two Dirichlet conditions, or two, just value, you can call them value conditions too if you want, okay? And so our basis functions have to satisfy those boundary conditions. And it turns out they did, right? If you look at our original basis functions right here, then you see that sine of n pi times 0 is always equal to 0, and sine of n pi times 1, so sine of n pi, is also equal to 0 because you can go around the unit circle and show that sine of n pi whenever n is an integer is always going to be 0. Okay? And that is how we were able to show that this term here is equal to 0. Because our basis functions are always going to be 0 when y is equal to 0, and is always going to be equal to 0 when y is equal to 1. Okay? And then this third guy right here, this third term was always going to be equal to 0 because of our boundary conditions, right? Our boundary conditions for g said that y is equal to 0, or said that g is equal to 0 when y is equal to 0, and g is equal to 0 when y is equal to 1. And so that's how this last term is equal to 0. I don't know why that says u for g. Okay? And that's how we were able to do this magical integration by parts step. If you recall, right, the left-hand side of this is that we just transformed we got a time derivative, but then the right-hand side, we were able to basically take this derivative in y and then turn it into something that's not a derivative at all anymore. And that's how we were able to take the PDE and turn it into an ODE. Okay. Now there's one more property that the basis functions have to satisfy. The basis functions have to be orthonormal. In other words, just to remind you, orthonormal means this. Right? When you multiply two of them and you integrate them, then you always get either 0 or 1, depending on whether those two basis functions are equal or not. Okay? And so that's how you find the basis functions. Okay? You basically apply these three properties, and these three properties actually specifically determine unique basis functions for what would be useful for our problem, right? Let me show you how we could have done that a priori. I'll say we can find the basis functions for our problem. Okay, so above I kind of cheated because I knew what the basis functions were, and so I just went ahead and just told you, right? But if you didn't know, if you're working on homework or something, it doesn't tell you these are what the basis functions are, then here's how you could actually find them, right? You apply the three properties, basically. The first property is that it has to satisfy this eigenvalue problem, okay? So in our particular eigenvalue problem, we basically have, this is the second order differential operator, and so we have this, and it has to equal negative lambda n squared times phi n. And so like this. This is an ordinary differential equation. You can solve it, right? And so let's go ahead and solve that. The second order differential equation looks like this. Okay, does anyone know what the solution to this differential equation is? Just off the top of their head?
It's a plane wave like combination. Um,
You can just say sines and cosines, right? Yeah. Okay. And for now, let me go ahead and erase these ends here because they're not going to be important until later on. Okay. We can apply the boundary conditions now to actually figure out what the values of a, b, and lambda are going to be, right? Ooh, I don't know how that got all the way over there here. Okay, and so that's requirement number 2. Requirement number 2 is that they must satisfy boundary conditions of the same type as our original problem. Our original problem said that g is equal to 0. It's that the value of g is equal to something at y equals 0 and y equals 1, right? And so what we have here then is 2 boundary conditions. I'll call them BC1 prime. That's that phi is equal to 0 and y is equal to 0. And BC2 prime, which is that phi is equal to 0 and y is equal to 1. Again, same type as what we had. If our original problem had that g is equal to 0 at y equals 0, and then dg dy is equal to 0 at y equals 1, you can imagine why that would be the case, for instance. Maybe you have a no stress condition somewhere in your problem, right? Then you would need to make sure that this is phi is equal to 0 here, and then d phi dy is equal to 0. You would have a Neumann condition here, okay? But again, you apply these boundary conditions, and then you can get your actual solution, okay? If we apply boundary condition 1 prime, for instance, that gives us that 0 is equal to a times sine of lambda times 0, because that's at y equals 0, plus b of cosine lambda times 0. Okay? Sine of 0 is equal to 0. Sine of 0 is equal to 0, right? And then cosine of 0 is equal to 1. And so this basically implies then that b is equal to 0. Okay? Boundary condition 2 is that 0 is equal to a times sine of lambda times 1, because that's where y is equal to 1, right? And this implies then that lambda is equal to n pi, where n is equal to 1, 2, 3, etc. This is where we go around the unit circle, right? You guys hear that? Sorry about the, yeah. Okay. So this is where the unit circle comes in, right? Because if you know that sine of lambda is equal to 0, then lambda has to be either, 0 here, or 1, or 2 pi, or 3 pi, etc., right? And so this is how we actually get the values of the eigenvalues here. This is where our lambda n comes in. Okay, and so there are infinitely many solutions. Right? Those solutions look like this. Okay. And then it's the third condition here that then gives us what the values of a sub n are. Okay. It's that these solutions have to be orthonormal. Did someone say something?
Yeah, I just had a quick question. So wait, I might have missed it. Why again does n start at 1 and not 0?
Oh, you could start at 0, but that's not helpful
Okay.
because sine of if n is equal to 0, then that basis function is just 0, right?
Right,
And
right.
so that's
Okay.
not a real basis function that's helpful at all, right?
Got it.
Yeah. Okay. And so number 3 is that we need to make sure that the basis functions are orthonormal, right? And so what I'll say is that it turns out that these functions are already orthogonal. Orthogonal meaning that the inner product is equal to 0 if n and m are not equal. Okay? If I were to take this integral here, like that, you can go home and show that, or not go home, sorry, you can stay at home and convince yourself that this is equal to 0 if n does not equal m. Okay, just pop up Mathematica and then just type this in for a few different values and you'll see the pattern. This is always just equal to 0 if n does not equal m. Okay. To make them orthonormal, then we need to pick values of a sub n. Okay. In other words, if I calculate this, this should give me 1, right? The value of this integral looks like this. And this has to equal 1 to make everything to make the basis functions orthonormal. Okay? And if I were to actually calculate this integral and stuff, and then solve this equation right here for a sub n, then what I find is that a sub n is just equal to the square root of 2. Okay, this is called normalizing a basis function. Okay, it's kind of like normalizing a vector. For instance, if I give you a vector and I want you to find another vector that's pointing exactly in the same direction, but only has a magnitude of 1, then you just calculate the length of that vector and divide the whole vector by that value, right? That's essentially what I'm doing here. I'm taking a basis function and dotting it with itself, or doing an inner product of itself. So in other words, calculating the magnitude of that basis function, right? And I'm just dividing through by that. And so I'm letting my a sub n be square root of 2. Okay, and so therefore, that's how in this case, our lambda n, or phi of n, is equal to sine of n pi y. Okay. It's 4 o'clock. The last thing I'll mention is that these basis functions are different for different PDEs and boundary conditions. And it turns out that there aren't actually that many different choices of PDEs and boundary conditions, right? Like there's a finite number. I showed you guys that there are some Dirichlet boundary conditions and Neumann boundary conditions and stuff like that. And so instead of actually going through the process of finding what the basis functions are, a lot of times you actually just look them up. Okay, so go to Dean, table 5.2, and it'll actually show you. I'll try and find it real quick right now. I think I have a copy of Dean right here. It'll actually show you what those basis functions actually are. Table 5.2, come on. If I can find it. Can you guys see that? This is page 168 in the most recent edition. And at the bottom is table 5.2. You can see those basis functions right here, right? I'm sorry, this is a terrible way of actually showing you guys, but you can see in the first row right there, right? It says the two boundary conditions of the basis functions are where the value of the function is equal to something, as opposed to the value of the derivative is equal to something, and that tells you what those basis functions actually are, right here, right? And you should hopefully see that that's something like square root of 2. It has everything in terms of an L, like our h here, but in this case we set L or h is equal to 1, and then it has the actual basis functions that we have. But then of course you have other cases, for instance, if the derivatives are equal to something, or if one thing is equal, if one side is the derivative and the other side's value is equal to something, then it has all sorts of different basis functions that you can use. And again, you can calculate these also using basically the process that we just talked about right now in class. Okay, all right. I'm gonna stop right now. We're actually a little bit over on time. I apologize for that.